All right, ladies and gents, I wanted to try to work out a few problems. And for those few problems, I wanted to see if we could just focus on the graphing problems. So I pulled up the practice graphing motion assignments and I just saved all 6 problems. We'll take a look at them. And I can additionally flip over to the actual quiz and we can take a look what the answer options are and type it in and see what we get as a score. So let's do it. First off, we have a position versus time graph. On position versus time graph, the slope of any line segment is always going to be equal to the velocity. In this case, it's saying calculate the average velocity for the object whose position time graph is shown for 5 to 8 seconds. So that means we start at 5 seconds and we read what the position is. It's going to be 4. And we look at 8 seconds and we read what the position is, and it's 8. And we just want to calculate the average velocity during that time interval. That means we're looking for the slope during that time interval. And slope is always rise over run. But when we're dealing with a rise, we're looking for the change in the vertical value. Since it's positions, that's change in x, delta x. And the change in the horizontal variable, the run, is change in time. So change in position over change in time, that's why slope is equivalent to velocity. It's nothing magical, just because the equations line up with each other. So here in my change in position, I'd have 8 minus 4 meters, and I'd have for change in time 8 minus 5 seconds. So 4 meters over 3 seconds, that would be 1.333333. That's my velocity. So I'm going to go ahead and type that in right here. See if we're right later. Oops. Too many things. Okay, let's take a look at number 2. Number 2, I believe, wants us to pick between graphs. So we'll see if we can draw a graph here for velocity versus time, and then see which ones match up. In this case, the first segment that we've got here, it would have a slope of 0. There's no slope. So that means the velocity is equal to 0 for the first 5 seconds. And then the second segment, it looks like we're going from time 5 to time 8. That'd be a delta t of 3 seconds. And the change in position we have during that is 6. So we'd have 6 meters over 3 seconds would be 2 meters per second. So we'd want a velocity versus time graph that's got nothing for the first 5 seconds. So if I draw time versus velocity here, for the first 5 seconds, nothing, and then from 5 to 8, we're going to have a positive 2. So let's write some of this out here. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5. And then it's 1 and 2 right there. So that's 0 velocity, 0 seconds. And so we should get something, draw with green for the first 5 seconds, flat line, and then it jumps up to 2 for the next 3 seconds. I'm not sure what the scaling is going to look like on our answer options, but that's what I would expect it to look like, a nice step like this. So let's see what we got. My answer options down below. Oops, got to go to the next question. So I've got nothing for 4 seconds and then that's not it. Ooh, 5 seconds and then, ooh, yep. Oh, wait, hold on. That's just 1. Pretty sure it's supposed to be 2. There we go. So from 0 to 5 seconds, we got no velocity, and then from 5 to 8, we've got 2. So that should be correct. Let's go to the next problem. Our problem number 3, now we're given a velocity graph. We're asked for the total displacement. All right, well, we were just doing this in class today. The displacement should be equal to the velocity multiplied by the amount of time that goes by. And for each line segment, that's going to represent the area that is bounded between the time axis and the velocity graph. So for that first 2 segments, we should have it's a positive velocity. We should have some displacement. For the second segment of the graph, there's nothing. There's no area right there, which would translate to 0 meters per second. multiplied by the number of seconds there. There's 3 seconds go by. So we get nothing. For the first area, I apologize, I forgot to write that in there. We should have a velocity of 2 for 2 seconds. So that'd be 4 meters. And then the final, this is the tricky one, that we tend to have problems with when we review these. The displacement is going to be the velocity, which is -1, multiplied by the time of 3 seconds. So I'd have -3 in that case. Now, the answer for this is we wanted to calculate the displacement for the first 8 seconds. So 0 to 8, that's the time we're looking for. So we've got +4, nothing, -3. If we just add all those up, 4 plus 0 plus a -3, we should get 1. So we should have a displacement of 1 in this case. We went forward 4 meters, stood still, and then went backward 3. So let's see here. For this problem, let's go and just type in 1. Oops, I typed in 21. That would be bad. Let's go to the next problem. Okay, another velocity graph, another total displacement. This one's a little trickier. We got 3 segments here. We want, again, displacement. So same procedure, nothing crazy. This one just, because we have 2 different velocities right next to each other, sometimes people get a little mixed up when they're calculating the displacements as the areas. But for that first area, our delta x would be equal to velocity 3 multiplied by a time of 2 seconds, or 6 meters. And for our second displacement, or second amount of displacement, it looks like we got a velocity of 1 meter per second, and that's going from 2 to 1, 2, 3, so 3 seconds of time, or 3 meters. And then at the end there's going to be no displacement because it's got a 0 velocity. Add them up, should get 9. 9 meters total displacement. Let's type that in. Whenever I do these things, I start to worry that I'm going to get all the answers wrong. Very nerve-wracking. It happens sometimes. Fairly rare, but it happens. All right, so question 5, we've got a velocity versus time graph, and we're asked to pick a position graph. So if we go back to the actual quiz, there's a bunch of position graphs. Everybody loves these, right? So we're going to try to draw a position graph for this, and then see if we can find the correct one from the list available in the problem. First off, we need displacements. In this case, we got 0 meters displacement for the first 5 seconds, and then the area bounded between the velocity line and the time axis for this problem, the delta x. Let's see, we got 2 meters per second. I just wrote a 3. I think we call that a boo-boo. So 2 meters per second, let's look across there, it's at 2. And that happens for 1, 2, 3 seconds. Again, if you're always stuck on the delta t, the amount of time that goes by, it is a delta. It's the new minus the old. The new time is 8 seconds, the old time is 5, 8 minus 5 is 3. Whenever you're stuck, just go back to that old idea that it's a delta t, it should be a change in time. It's not how many markings are on the meter stick or on the time axis there. It's how many you've moved from your initial moment to your last. So we should have 6 meters. So I would expect to get some sort of position graph. We'll draw it as if it starts at position 0. It doesn't have to. But if I've got time and I've got position here, let's say it starts at 0. In the first 5 seconds, I'd expect to do nothing. 1, 2, 3, 4, 5. So I just have a flat line. And then for the next 3 seconds, let's say that's 5, and then 6, 7, 8, I'd expect to go forward 6 meters. So I know I'm just kind of not labeling everything here, but I'd want it to look something like this. Something along those lines. Along those lines, hey, it's a pun. Let's take a look at the answer options we got. First one, it's almost promising, but the first 5 seconds we're supposed to have no movement, so that's clearly not right. Here we go, first oh wait, no, that's wrong because it's 6 seconds of no movement, and then in 2 seconds we go 8 meters. Well, that's not right. 5 seconds no movement, 3 seconds we go 6 meters forward. That's looking pretty good. Double check the last one. Yeah, the last one. While we have no movement in the first 5 seconds, we only go forward 4 meters. So this one does not have the right displacement. It has a correct ending position if we started from 0, but if this were the case, we'd have to go up to 8 meters. So this would be the correct one. All right, let's see. We got one more problem here, I think. So another velocity graph. And this one we're asked to find the position graph again. But this one's got that little bit of trickiness. We got that negative position change. First area we got here, that's going to be a delta x of, let's see, 1 meter per second multiplied by 4 seconds, or 4 meters. And then the second area, that's going to represent a displacement of negative 2 meters per second for 2 seconds, or negative 4. And then the last bit is going to be no displacement. So we'd want a position graph that increases in position and then decreases in position and then stands still. So if we were to start from 0, we'd want, let's see, we're doing 8 seconds again, might as well write that all in here. 1, 2, 3, 4, 5, 6, 7, 8. Let's see, 1, 2, 3, 4. We want in the first 4 seconds to go up to position 4. Like that, looks pretty good. And then we want it to decrease 4 meters in the next 2 seconds. Like this. And then stand still. So kind of a weird triangle spike here. And I'll be honest, I wrote all these problems and I don't remember making one like this. So let's take a look. We got a triangle, all right? This goes 4 meters in 2 seconds and then negative 4 and 4. Okay, so it's kind of reversed. This one's clearly wrong. This one, let's see, 4 seconds, 4 meters. And then the next 2 seconds, negative 4, we go backwards. So that's looking good. And this is looking funky. So yeah, it's going to be this one right here. All right, moment of truth. Answered all 6. Did we get a 6 out of 6? Let's find out. Yep, got 6 out of 6. All right, so all this setup that we just did here in the last 12.5 minutes or so, similar problems, you can go through and do that quiz again, or you can do that 23 question quiz if you're feeling a little crazy. But that's how we set up some of these position and velocity time graph problems. Best of luck to you.